Hi class. For this clip, I'm using a handout. Sorry, I got caught a little bit off guard. Just want to make sure I'm referring to the correct file name. Oh shoot. Okay. Yeah. This is just introducing the chi-square statistic. I'm using a handout. This one also has, this portion of the handout also has 2 pages that look like that. We'll get to both in a second. But the first thing I want to introduce you to is the symbol. When we're referring to chi-square analysis or chi-square as a statistic, this is a symbol that we'll use. As you can see, it's kind of a funky X, and it has an exponent 2, which means to square, chi-square. So whenever you write chi-square as a statistic or as a symbol, this is a symbol you should use without the quotes. You do not need the quotes. In fact, please do not put the quotes in there. I just put the quotes to let you know this is the literal symbol, chi-square, okay? In addition, what chi-square measures? This is what chi-square represents, and this is a very important piece of information to keep in mind because we've used it before. What does T represent? Units of standard error. What does Z represent? Units of standard deviation. What does F represent? ANOVA, units of between group variance. What does chi-square represent? Well, as you can see from this handout, chi-square represents or measures the difference or distance between 2 things. And those 2 things are observed cell frequency and expected cell frequency. Now we're going to get into very shortly, I promise you, we're going to get into what we mean by cell frequency. But as you can see from this handout, there are 2 types of cell frequency. There's observed cell frequency, which is a little primer I'll tell you up front. Observed cell frequency is simply that which we observe. That's simply how, another way to refer to it is how the data fall. Just, again, what we observe. So like if we were to go out and conduct a survey or do a study or collect data from some sources, the observed frequencies would be how the data fall, period. The other type of cell frequency, as you can see from the handout, is the expected cell frequency. Now the expected cell frequency we're going to have to calculate, pretty easy to calculate, but it takes a little bit of work, but again, it's easy. But what's more important at this point in time is that I introduce you to what we mean by the expected cell frequency. The expected cell frequency is how the data would fall if there were no relationship between the 2 variables you're analyzing. Again, the expected cell frequency is how the data would look or how the data would fall if there was no relationship. So, reviewing very briefly, chi-square as a number represents the difference or the distance between 2 things, and those 2 things are observed cell frequency and expected cell frequency. Observed cell frequency is simply how the data fall, what our data look like after we collect it and put it into a contingency table, which again we'll get to very shortly. Expected cell frequency is how the data would fall if there's no relationship. So chi-square measures the distance or the difference between those 2 things. How much distance is there between observed cell frequency and expected cell frequency? Now, continuing on with this handout, in keeping with all the other statistical tests we've been conducting, we are going to use 2 sources of chi-square values. 2 sources of chi-square values. And I hope that there are no surprises regarding what these 2 sources of chi-square values are. One is going to come from our data, and as you can see, data generated. The second source of chi-square values is going to be the tabled chi-square value, which is going to come from the chi-square probability distribution, a table in spats, just like every other test that we've conducted so far. So this right here, we're going to deal with two different types of chi-square values, or two sources of chi-square values, data generated and tabled. That's the same thing that we've been dealing with for every other statistical test that we've conducted so far. Now the second page of this handout, I go into a little bit more detail as a primer, if you will, in terms of how to refer to the different sources of chi-square values. Again, data generated and tabled, right? We already established on page 1 that we're dealing with, that we will use two sources of chi-square values. One's going to come from our data, the other's going to come from the table. And then here, the second page, I just came up with a generic example, a generic example of how to refer to those two different sources. So looking at the top of that second page, for example, assume our data generated chi-square value is 4.25. So in other words, assume we've learned how to calculate chi-square, we've utilized the data, we've set up the problem, done the math was done correctly, and when all is said and done, we come up with a number. And that number is 4.25. So I just pulled that out of thin air, came out of my head. Data generated chi-square value of 4.25, we would refer to, or we would say, in order to describe that result, there were 4.25 units of difference between our observed frequencies and our expected frequencies, period. So again, you already learned on page 1 that chi-square is simply a measure of the difference between two things, and those two things are observed and expected frequencies. If our chi-square value were 4.25, this is how we would refer to that value. There were 4.25 units of difference between our observed frequencies and our expected frequencies. So that's just wording. That's wording that you would use to refer to data generated chi-square. Tabled chi-square, and again, I just used a generic number. I pulled this number out of my head. Tabled chi-square, let's assume that tabled chi-square value, well, first of all, let's make some more assumptions. Let's assume that we've talked about the chi-square table, learned how to use it, and have picked a value, picked hopefully the correct value from that table, and that correct value is 2.84. Tabled chi-square equals 2.84. This is how we would refer to that value. The maximum amount of difference between observed frequencies and expected frequencies is 2.84. Given the degrees of freedom, I realize we haven't yet talked about degrees of freedom, but we will, given the degrees of freedom and the size of the critical region or tail. Now, the reason I'm introducing this now, even though we haven't even looked at the table, we haven't even talked about the math involved in chi-square, is because this sentiment, this statement is very much like every other inferential statistic that we've done so far. Whether you're talking about t, whether you're talking about f, whether you're talking about chi-square, the values that are in those tables, those probability distributions, those values are the maximum, this is very important, the maximum amount that you could expect to occur by chance given certain conditions. The maximum amount, whether you're talking about t, whether you're talking about f, whether you're talking about really z in a sense too, or in this case chi-square, those values in the table represent the maximum amount that you could expect to occur given certain conditions. And what are those conditions? Degrees of freedom, which comes in a number of different forms, and the size of the critical region. Okay, next we'll be moving on to the chi-square probability distribution. So this was just an intro to the chi-square as a statistic and some of the language used to refer to it.